Hello everyone, I'm Ethan Zhang, and I am a PhD student at the University of Michigan. Today I'm presenting our work, a learning-based method for predicting heterogeneous traffic agent trajectories, implications for transfer learning. So the past decade has witnessed the rapid development of autonomous vehicle technology, and accurate trajectory prediction can be one of the key components to improve the safety of both autonomous vehicles and its surrounding traffic. Autonomous vehicles need trajectory prediction to plan routes and avoid potential collisions, while other agencies like transportation management agencies can use accurate trajectory prediction results to issue alerts to improve the safety of transportation systems. Trajectory prediction for different types of traffic agents can be a challenging task for different reasons, such as the complex nature and the heterogeneity of traffic agents, the dynamic traffic environments, and so on. In this paper, we use a learning-based approach for trajectory prediction for heterogeneous traffic agents, which includes pedestrians, vehicles, and cyclists. And we also investigate the benefits of transfer learning on this topic. There's some existing work focusing on predicting trajectories for different types of agents. However, the existing work suffers from one or more of the following drawbacks. First of all, they build agent-specific model architectures for different agent types. For example, designing specific model architectures for pedestrians and vehicles, which can be time-consuming and harder to maintain if deployed in real world. Secondly, some of them use discretized output space, which can handle prediction accuracy because in real-world scenarios, trajectories are continuous. Thirdly, some work are only able to provide accurate prediction in short horizons, such as 2 to 3 seconds into the future, and some of them are very sensitive to model parameters. Last but not least, some of them have high information requirements. For example, these models require information of all agent presence in the scene. In contrast to existing literature, in this paper, we propose a genetic model to predict trajectories of traffic agents regardless of their types. Unlike methods that require information from all agents in the scene, our proposed model only uses history trajectory information of the subject agents and learns patterns within those trajectories and then predicts the future positions of subjects within a finite horizon. The common architecture used in this study includes a combination of RNN and CNN kernels. The input to the architecture includes two-dimensional local coordinates of the history trajectory of an agent. First of all, an LSTM-based RNN kernel is used to process the raw trajectory inputs and learn time-related patterns. The patterns in each time step are learned by a time-distributed kernel with a CNN-based encoder. In the time-distributed kernel, patterns of each time step are distributed into a squared tensor and then fed to an encoder based on CNNs and an augmented attention, which is used to capture global information from the CNN outputs. And GRU based on an kernel is then used to decode the learned patterns in the previous kernel. Finally, the architecture outputs the position of the agent within the next time step. Using a sequential prediction strategy, we can get a predicted trajectory given a desired prediction horizon. Unlike existing learning-based models that develop agent-specific model architectures, we use a generic architecture and train the architecture on pedestrian, vehicle, and cyclist dataset respectively to obtain agent-specific models. To evaluate the proposed approach, we compare its performance against the extended common filter, which is a general trajectory estimation method. We evaluate the model over two metrics, the average displacement error and the final displacement error. We conduct the experiment over an open-source dataset provided by Lyft. After processing, the training set we use for vehicle model contains 450,000 trajectories, and the pedestrian set contains around 190,000 trajectories, and cyclist training set size is around 30,000 trajectories. Here we are showing the model performance. For 5-second prediction, the ADE for pedestrian trajectory prediction is 0.89 meters, the FDE is 2.58 meters, and the FDE for vehicle is 2.95 meters with the FDE 7.03 meters, and the ADE for cyclist model is 5.96 meters, and the corresponding FDE is 14.80 meters. Based on the results of the proposed approach, the ADE of the pedestrian trajectory prediction is around a single step length of an adult, which is around 0.71 meters to 1.49 meters, and the ADE of the vehicle trajectory prediction is less than the average vehicle length, which is around 4.20 meters, and the ADE of the cyclist trajectory prediction is about 3 times of the average bicycle length, which is around 1.70 meters. The lower performance of the cyclist model compared to the vehicle and pedestrian models can be attributed to its smaller training sample size. The performance of the proposed model against the EKF benchmark during the prediction horizon is also demonstrated in the figure. The rate of increase in the displacement area of the proposed model is significantly lower than that of the EKF model, resulting in the gap between the displacement area of the two models to grow superlinearly with time. The performance of deep learning tasks can be related to the size of available training data. As aforementioned, the size of the cyclist trajectory dataset is small as it's a less commonly used vehicle in the real world compared to pedestrians and vehicles. A main benefit of the proposed work is that, as a result of using a common model architecture for all agent types, transfer learning can be adopted to improve the prediction performance of cyclists. Here we investigate the transfer of the learned knowledge from vehicles and pedestrians to cyclists. This is also a main advantage of the proposed model. In this slide, we are showing the transfer learning details. The left two figures show the training loss when the cyclist model learns from vehicle model and pedestrian model respectively. Red lines are validation loss, while blue lines are training loss. We see an increasing in training and validation loss at the beginning when the transfer learning starts, but later we can notice a decreased trend in the training loss when the transfer learning continues. The rightmost figure shows the training loss comparison between model using transfer learning and the original cyclist model, where the red line shows the original loss statistics, where the blue and green lines are loss statistics of transfer learning from vehicle and the pedestrian model respectively. As can be noticed from the figure, transfer learning provides better training results, which means the performance can be actually boosted. In this part, we are showing the transfer learning result. The left figure shows the comparison between different models in terms of the displacement error across different prediction horizons. Conducting transfer learning from the pedestrian model results in best performance compared to other models. The corresponding FDE for 5-second cyclist trajectory prediction is reduced from 5.96 meters to 1.43 meters, and the corresponding FDE is reduced from 14.80 meters to 3.74 meters, which is a great improvement. And conducting transfer learning from the vehicle model reduced the FDE to 2.86 meters, and the corresponding FDE is reduced to 7.30 meters. An observation from this result is that, although the vehicle trajectory dataset is larger than the pedestrian set, it does not produce the best transfer learning performance for cyclist trajectory prediction. This is because the performance of transfer learning is also affected by the similarity between the source and target tasks. We use the probability distribution of the distance between two adjacent positions for each agent type to represent the task property, and use callback library divergence to compute the similarity between tasks. The lower the KO divergence score, the higher the similarity. This, this distribution captures the moving velocity of agents, which is one of the most basic patterns of behavior attributed to traffic agents. Based on this distribution, the KL divergence of pedestrian to cyclist task is 51.15, while that of vehicle cyclist task is 127.76. These scores explain the performance difference of transfer learning result, which is that the pedestrian to cyclist transfer learning task is more desirable as the source and tag tasks show higher similarity. In this work, we utilize a learning-based approach to predict trajectories of pedestrians, vehicles, and cyclists in long horizon. The proposed approach does not construct different model architectures to develop agent-specific models. Instead, it generates agent-specific models by training a common architecture over agent-specific datasets, rendering it more desirable for practical applications. We compare the model with extended common filter. Experiment result indicates that the proposed approach outperforms the EKF benchmark in 5-second prediction horizon in terms of both average and final displacement errors. The generic architecture also benefits from transfer learning. We demonstrate that by transferring knowledge from pedestrians and vehicle datasets, which are larger in size, the prediction accuracy on cyclists can be significantly improved. And we also show that the performance of transfer learning is actually also affected by the similarity between source and target tasks. Thank you all for listening, and I will be happy to answer any questions.